Center of mass. By the end of this lesson, we'll be able to describe the behavior of a system using conservation of linear momentum, using an isolated system's center of mass. Center of mass is a point where the total mass of the system can be thought to be concentrated. It's a weighted average of the positions of all the particles in the system, weighted by their masses. Linear mass density is mass per unit length. The unit is a kilogram per meter, and oftentimes we'll see linear mass density use the symbol lambda. We'll look at that later. Center of mass happens to be in anything with mass. It's often for a uniform object where the density is constant throughout the entire object. It's going to be right exactly in the center. For something that's not uniform, there are some calculations that you would need to do to figure out where the center of mass is. So a collection of objects with individual momenta can be described as one system with one center of mass velocity. That's for one object, there would be one center of mass. For two objects, there would be one center of mass. To find the position for a center of mass, we're going to use this equation, which is x of the center of mass equals sigma m times x divided by the sum of all of the mass. So the sum of each mass multiplied by the position each mass or object is relative to a reference point. Could be the origin of a coordinate system, it could be the end of a rod, the end of a stick. It's an arbitrary position as long as you keep it 0 the same time at the same place, the math will work out. It's an arbitrary position where as long as you keep 0 in the same place throughout the entire problem, everything's going to work out. The total momentum of a system is the sum of the momenta of the system's constituent parts. To find the velocity for a center of mass, use this equation. Velocity for center of mass is the sum of mass times velocity divided by the sum of mass. This can be derived from the conservation of momentum. So hopefully that looks familiar to you if you multiply the sum of the mass to each side. To find the acceleration for a center of mass, we can use acceleration for a center of mass equals sigma ma over sigma m, which is just the sum of the forces divided by the system's mass. When do we use this center of mass? When we're asked for the position, velocity, or acceleration for a system's center of mass. In many problems, especially those involving complex systems, it's easier to consider the motion of the center of mass rather than dealing with every individual particle. We've done this before, earlier in the year, when we shrunk objects like a car down to a point mass. We were just tracking the movement of a car's center of mass. In celestial mechanics, when we were looking at the orbits of planets and moons and artificial satellites, we talked about the motion of their centers of mass. Coming up, analyzing rotational motion. The rotational dynamics of a body, including its angular momentum and angular energy, are often calculated with respect to its center of mass. Here's an example. The student is given a task to find the center of mass of a composite object. The object consists of two small spheres and a rod connecting them, so kind of like a dumbbell. Sphere A has a mass of 2 kilograms and is located at the origin on an xy plane. Sphere B has a mass of 3 kilograms and is located at 4, 0, the ordered pair. The rod connecting them is massless and runs along the x-axis. Calculate the x-coordinate of the center of mass for the system. Very straightforward. Because our first mass is at position 0 in the x-axis, we use 0 as our position. Our second object is at position 4, so we use 4. Multiply them, and we get 2.4 meters from the origin. Imagine you have a rod of length 2 meters, which is not uniform. One half of the rod has a linear mass density of lambda 1 equals 2 kilograms per meter, and the other half has a different linear mass density, lambda 2 equals 4 kilograms per meter. Find the position for the center of mass of the rod. First thing we need to do is define the mass for each section of the rod. The first section will weigh 2 kilograms, while the second section weighs 4 kilograms. We did that just by multiplying the length of each section by the linear mass density. Each length is half of the rod, and the full rod is 2 meters, so each length is 1 meter. Next, we're going to define the position for the center of masses for each section. The center of the first position is halfway through the first section. If the first section is 1 meter long, then halfway through that is going to be at position 0.5, and for position 2 is going to be at 1.5 meters from the end. Next, we'll calculate the total mass of the rod to be 6 kilograms. And finally, we'll calculate the position for the center of mass using our formula, and we should get 1.16 meters from the left end of the rod. Example 3, in a physics lab experiment, 2 carts A and B are on a frictionless track. A has a mass of 3 kilograms and moves to the right at 4 meters per second, while cart B has a mass of 2 kilograms and moves to the left at 2 meters per second. Calculate the velocity for the center of mass for the system comprising of both carts. Another straightforward one. We're just going to use our velocity for center of mass equation, plug in our numbers. Don't forget that negative. Next steps, complete practice. For more practice, there's your AI prompt. Limit movements to 1 or 2 dimensions here. Don't forget that if we're dealing with 2 dimensions, then momentum needs to be conserved in both dimensions. X and Y, for example. We need to treat X momentum separate from Y momentum. And all of the momentum in the X direction should be conserved, and all of the momentum in the Y direction should be conserved, as long as there is no impulse acting on our system. Finally, make sure you have these 3 equations that we went over, the position, velocity, and acceleration for center of mass, memorized because they're not on your equation sheet. Ask each other, ask me for help, keep asking until you get it.